So let's finish our discussion of vectors in space. We're going to talk about planes now. So planes are determined by a point, x1, y1, z1, and by a normal vector, which is a, b, and c. And so then you would write the equation of a plane as a x minus x1 plus b y minus y1 plus c z minus z1 equals 0. So this would be an equation of a plane. So let's look at an example here. Find an equation of the plane containing the points 2, 1, 1, 1, 4, 1, and negative 2, 0, 4. So the first thing I'm going to do is give these vectors names. Here's P, here's Q, and here's R. So kind of the setup we're working with, I'll just draw a brief picture. Here's P, here's Q, and here's R. And so what we can do is form the vectors PQ and PR. So these are going to be vectors that are in our plane. So let's go ahead and form the vector PQ. Remember, it's terminal minus initial. And then 1 minus 1. So this vector would be negative 1, 3, 0. And then PR would be the vector negative 2 minus 2, 0 minus 1, and 4 minus 1. So here I'm getting negative 4, negative 1, and 3. So then you want a normal vector for the plane. So you can find a normal vector. Remember, it's orthogonal to the plane. It would need to be orthogonal to both these vectors. So to find our vector n, you're going to take the cross product of these two vectors. So here, I'm going to take the cross product of I, j, k, negative 1, 3, 0, negative 4, negative 1, 3. So here we compute this cross product. We'll get 9i minus negative 3j plus 1 minus a negative 12, so 1 plus 12k. So I believe you get 9i plus 3j plus 13k, assuming I don't have any arithmetic mistakes there, which maybe I do. So once you have your normal vector, all you need is to go back and pick one of your 3 points. I'll just go back and pick the point P, which was the point 2, 1, 1. And then you can write the equation of your plane. So it would be 9x minus 2 plus 3y minus 1 plus 1 z minus 1 plus, not 1, 13. 13 z minus 1 equals 0. And you could distribute that out, or you could just leave it like that. All right, so then we talked in our last bit about cylindrical and spherical coordinates. So I want to mainly focus in on reminding you what these are and what the conversion equations are. So cylindrical coordinates, you represent a point in 3-dimensional space as r, theta, and z. Now, these r and theta are the same ones you get when you're talking about polar coordinates. Our conversion equations are x equals r cosine theta, y is r sine theta, and remember when you're in rectangular, you normally have a point represented by x, y, z, so the third coordinate is the same between the 2 points, so z is z. And then the other conversion equations for converting in a different direction are r squared equals x squared plus y squared. Tangent of theta is y over x. And the third coordinate again remains the same. So these are our 2 sets of conversion equations. So let's look at an example. Let's convert the point r theta z, which is going to be 4 pi over 2 and 3 to rectangular coordinates. Well, that means I need to write my point as x, y, z. Well, I already know z, right? Z is 3. So I've already got a head start here, x, y, 3. So all I have to do is find x and y, use our conversion equations. X is r cosine theta, r was 4, cosine of pi over 2, which is 0. Y is r sine theta, 4 sine of pi over 2. Sine of pi over 2 is 1, so it's 4. So now we've converted the point. It's 0, 4, and 3. And that's my answer. So lastly, how do we convert from spherical coordinates? How does that system work? So remember, spherical coordinates is based on rho, a theta, and a phi. So rho represents the distance to the origin, or from the origin. Theta is the same as in cylindrical. The one new angle is phi, which represents the angle from the positive z-axis. So coming down from here, and this phi angle, it's between 0 and pi. All right, so how did we convert between spherical to rectangular? We had conversion equations. X is rho sine phi cosine theta. Y was rho sine phi sine theta. And z was rho cosine phi. So those were our first set of conversion equations. And our second set, so rho squared, it's a similar equation to the formula for r squared. Tangent of theta is, because theta is the same, it's still y over x. And then phi is our cosine of z over the square over rho, which is the square root of x squared plus y squared plus z squared. So these are our second set of conversion equations. So we're going to look at converting a point. Do one example here. Convert the point from spherical to rectangular coordinates. So the point would be the point 0, pi over 6, pi over 2. So this is our rho, our theta, and our phi. So we need to get the point in terms of rectangular x, y, z. So we're going to use our first set of conversion equations. X is rho sine phi cosine theta. Y is rho, I'm just going to write down all the equations, sine phi sine theta. And z is rho cosine phi. So plug in our angles here, or our, oh wait, I didn't mean for rho to be 0. Rho, I'm going to have rho be 2. So 2 sine pi over 2 cosine pi over 6. This is going to be 2 sine pi over 2 sine pi over 6. And this will be 2 cosine pi over 2. Cosine of pi over 2 is 0, so this is 0. Sine of pi over 2 is 1, so this is 2 times square root of 3 over 2. This is 2 times a half. So our point is going to be square root of 3, 1, and 0. So there's our point in rectangular coordinates.